Are you defining a cubic system as A equal to B equal to C and alpha beta gamma equal to 90, and similarly for the other system what it is given? Then it is wrong. We should not define a cubic system with these parameters, and in this particular video we will discuss how to define and how to classify the crystal system. We know there are 7 crystal systems like cube, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic and triclinic. The cubic system generally people define as A equal to B equal to C and alpha beta gamma equal to 90, and similarly it is given to the different crystal systems. But this is not the way to define a cubic system. There are certain fundamentals behind which the system has to be defined. We will discuss that in this particular video. The basic definition which we use as A, B, C are equal and alpha, beta, gamma equal to 90, for example for cube, it is not the definition because this is the parameters used for lattice or the unit cell of that respective system. Basically the A, B, C is representing the length of the unit cell. Similarly, alpha, beta, gamma says the relationship of this axis, that means it's the interaxial angles. What is the relationship among these axes? So this is basically defining the shape of the unit cell. It is defined with the length as well as with the angles. That's what this we should not use to define a cubic system. Here the next question comes, how to define or classify the crystal system. So we will see that how to define. Before we discuss further about the crystal system, we must know few fundamental concepts on the crystal systems. Those are lattice and unit cell. Let's discuss about the lattice. It is nothing but it's an invisible skeleton. It means this is an imaginary infinite set of mathematical points. So each point has an identical environment of all other. And if you see in this video, in this slide, that the bricks are placed in which there are certain points, the identical points are taken and which is represented by some kind of pattern. That pattern is called lattice. Here the crucial distinction, the pattern is a physical object, whereas a lattice is an abstract framework. We should understand this concept because this particular concept helps to understand the crystal system. We will discuss in detail about how this lattice gives as an important parameter in understanding this crystal system. Further, we will discuss what is lattice and its property. Already we discussed that lattice is a 3D periodic arrangement of points in space, and it must possess the translation symmetry. Translation symmetry is nothing but, suppose if I move this point to some other location with some vector and the pattern remains unchanged and it's symmetrically, the symmetricity also present along with this changed pattern. Okay, so this is the basic definition also to define a lattice. So the translation symmetry is a defining symmetry for lattice. So though the patterns are repeated, if the translation symmetry is not present, then we cannot say that is lattice. We cannot say that is lattice. So one should have in memory that if the translation symmetry is absent, then we cannot say as lattice. So this is very important point, should keep in mind whenever we are verifying, and in future we will discuss that why there are certain things are not qualified to say as a lattice. Here you can see the representation of 2D lattice and 3D lattice. By definition, we know the lattice is the periodic arrangement of points in space. It may be in 2D or it may be in 3D, but the repetition should occur in all the directions. So you can see in 2D as well as in the 3D pictures. Then here the next question comes, what is the distinction between lattice and crystal, or what is the relationship between the lattice and crystal? It's very simple. To define a lattice, we want only periodic arrangement of points. To define a crystal, apart from that lattice, we also need a atom that we say as motif or base. So when I place any atom in these lattice points, then it is said, then it can create a crystal. So that is a basic definition of the crystal or mineral also. It should be a definite crystal structures and inorganic substance. So inorganic substance means there must be some atom and definite structure. For that structure, it is need the basic structure from lattice. So this is the basic relationship between the lattice and crystal. Here you can see, if I place a atom in each lattice, then this kind of structure will be created. That is nothing but it is a crystal structure. So further we will discuss on this. Here we also can find the relationship in another pictorial form and its importance. So to define a crystal structure, we need two parameters. One is a lattice, another one is a motif. The lattice, it is representing how it is repeated or where the points are located in the structure, whereas the motif, it is what is repeated, what matter is repeated or what atom is repeated in that particular lattice. So it is how it is repeated and what it is repeated. With this we could able to make a structure of any matter or mineral. So here basically we are trying to understand the lattice is a skeleton, and also it must possess the translation symmetry. That means translation periodic points in space. If I place any atom in that particular lattice, then it is called crystal, that represent the body. So this must we must understand this distinction between the lattice and crystal. Further, we also can understand the distinction between the lattice and crystal. Already we discussed that lattice is a 3D periodic arrangement of points, and it is a geometrical concept and it has a geometrical property. Just like that, it's a length and angle. Those things we could able to measure from lattice. This is what here in the first slide also we saw that is a definition which we generally go to define a system. So it is a geometrical concept. A equal to B equal to C, that is a length, and alpha beta gamma, that is representing the angle between these lengths. Whereas the crystal structure is defined the 3D periodic arrangement of atoms. It is a physical object and we can measure the different parameters like density, specific gravity, weight of the particular that crystal. So also you could see in this particular picture, when I place representing with some kind of atom, for example chlorine and sodium, If I place that in the lattice, then only it is termed as crystal. Here, further, there is another important concept of unit cell, that is a building block of the crystal structure. Here, it can be defined as the smallest repeating parallelepiped that generates the full structure. That means again it is a repetition of that particular unit cell in 3 dimension. It has two different types, we will discuss that, and how it is repeated. This is the smallest repeating structure which we get from the crystal system. The unit cell is nothing but it is a fundamental building block of the crystal structure, and also we can define as the smallest repeated element in 3D as a parallelepiped or 2D as a parallelogram, which vertex are lattice points. So the lattice points and unit cells can be related in such a manner that there are some imaginary points. When it is having some shape, smallest fundamental block, then we can say it is a unit cell. These unit cells have two different types. One is a primitive, another one is a non-primitive. The primitive is nothing but it contains only one lattice point per unit cell. Those things are placed at the corner of the unit cell. The non-primitive, in addition to the corner point as in the primitive, there is an additional point also present in the unit cell. Further, these non-primitive are subdivided into 3 different types: face center, end center and body center. The further that end center may be a B, C. So we will discuss that what is a major distinction between the face center and end center in next slide. You can recollect I said in the unit cell only one point will be there in the primitive. So in the left side you can see how it is taken into the account of different points. If any points in the corner, it will be taken into 1/8 because the adjacent unit cells also accountable for that particular point. It's shared by the 8 unit cells, one at the bottom layer and one at the top layer. So 8 adjacent unit cells will share the corner point. That's why we take as 1/8. Whereas the points which is present in the face center, then it is shared by the 2 adjacent unit cells. So we have to take into the consideration of 1/2. If any points present at the body center, then it is taken as a 1 because it is not having any shared relationship with the adjacent unit cell. So in this way we have to take into the account when we have points at the unit cells. Here the primitive unit cells are shown. Here we have points only at the corner. Okay, if the unit cell contains points only at the corner, then it is called as primitive unit cell. And also in the down it is represented as 8 corners are there in the unit cell of primitive. This primitive unit cell, that 8 corners, and also we know it since it's shared by 8 different unit cells in adjacent unit cells, so we have to take as 8 into 1/8. So we will get 1 point in that particular primitive unit cell. So this is the representation of non-primitive lattices. Already we discussed there is a 3 different types. In similar to primitive one, here also the points other than the corners is also additionally there are points at face center. If all the face contains the points, then it is called face center. Suppose the points only at the opposite side of the face, then it is called end center. The opposite side, when I mention, it may be a faces, A axis faces or B axis faces or C axis faces. So only one particular opposite axis contains the points. The other two will be divide of any points. So this is a major difference between the face center and end center. And also we can understand that body center, the name itself represent, other than the corners, the body center also have additional point. So non-primitive means it's a simple to understand that other than the corners there is a additional point in the lattice. So it is called non-primitive lattices. And also there is how many points can be permitted in the each lattice are given as similar what we discussed in the earlier primitive cell. In case of face center lattice, we have 4 maximum points will have, because the corners takes 8 points. It's shared with 8 different units, adjacent unit cells, so 1 by 8, whereas the face center share 2 adjacent unit cells, so 6 into 1 by 2, so 6 faces are there. So totally we will take 4 points in a body in face center lattices. Similarly, the body center will have 2 points because the corner point is 1 by 8 and the center point which is not shared by any other adjacent unit cell. So it contains maximum of 2 points. Similarly, for end center also it will have 2 points. In this slide you can understand the basic coordination system. That means the vector from a corner along the edges of the unit cell define a basic vector of the lattice. So whatever we discussed in the earlier slides, that A, B, C, the relationships are basically defined at what distance or at particular direction of that particular vector, how it is repeated along the directions. So it is defined by these parameters as well as the angle at which it is get repeated, and what is the relationship between two different axes. So the lattice parameter is nothing but it is defining the length of this repetition of the points as well as the relationship between these interaxial angles. That's what initially we said. This kind of classification we should not use to define a crystal system, because the crystal systems not defined by lattice alone, there is an atom also must be present in the lattice. So the crystal system is nothing but it's a lattice plus atom. Since it is not valid or to define a with a lattice alone. And very interestingly, why we should not use lattice by defining their shape? Because this is a non-uniqueness of the unit cell. In a given lattice positions, we can make the different types of different shape of unit cells. In this example, we already able to see the square lattice, rhombic lattice and diamond lattice can be made from the single repeated pattern. So unit cell should not define by shape. Then the next question comes, how to define or how to classify these unit cells. That is the interesting part of this particular video. Then what is the real basis for classification of lattice? The lattice are classified on the basis of their symmetry. Symmetry is nothing but if an object is brought into self-coincidence after some operation, it's said to possess the symmetry with respect to that operation. In simply, if you want to define, if you do some kind of operation, that means you are rotating or making a mirror plane on that plane of symmetry or center of symmetry, if you are observing, how many times the self coincidence is appearing during that operation. That is what we say it is a symmetry. And here it is represented the 2D lattice, and we have the different symmetry operations already given with different notations. Here we have the rotation symmetry, reflection symmetry in addition to translation symmetry. Also in the earlier slide we saw this is a basic definition or defining symmetry of lattice. To say it is a lattice, it must have translation symmetry. So any lattice must have translation symmetry. Apart from that, there may be some other symmetry elements like rotations, reflection and inversion. So this kind of other symmetry also possible, but definitely the translation symmetry should present. In this example, you can see the 3D lattice of cube, and also you can see in the right side the different rotational axes present in cube. This particular axis, there are 4-fold symmetry and 2-fold symmetry and 3-fold symmetry you can observe from this particular cube. So from face center to opposite face center is a 4-fold symmetry. From diagonal, that means solid angle to solid angle, there is a 3-fold symmetry, and similarly from edge to edge there is a 2-fold symmetry. So in this way we could able to find different symmetry operation while doing the different operation in the crystal system. But there is a one particular thing we have to observe from this particular slide, that there are different while doing a different operations we must get different set of symmetry elements. Are all the symmetry elements is present in all the classes of that particular system or not? That is a very interesting point to understand why the basic definition of crystal system differ from what we discussed in the first slide. Though there are number of different symmetry elements are present in each system, but there is a defining symmetry. Okay, for example, if you take a cube, all the form or all the crystal classes of that particular system must possess 4 axes of 3-fold symmetry. Similarly, the tetragonal system must have only one 4-fold symmetry that we obviously we know that is a c-axis, whereas the orthorhombic system are defined by 3 2-fold symmetry. It must possess 3 2-fold symmetry. Similarly, the hexagonal system is defined by 1 6-fold symmetry, and rhomboidal class must have only 1 3-fold symmetry. There may be other symmetry element. For example, in cube there are 4 3-fold symmetry. That is a defining symmetry. It must possess 4 different axes of 3-fold symmetry, but in rhomboidal only 1. And the monoclinic system must have only 1 2-fold, whereas the rhomboidal must have 3 2-fold. And triclinic system is not defined by any of this defining symmetry, but you should aware that to define a lattice it must have one symmetry, that is nothing but it is a translation symmetry. So if someone has to define a triclinic system, you can simply say it is must have only translation symmetry. Other thing is not required to define a triclinic system. In a summary, we can understand that lattice is defined by translation symmetry, and it is a repeated pattern in 3 dimension or 2 dimension, whereas a unit cell is a fundamental building blocks required to develop a crystal structure, and it is defined by the different parameters in terms of length as well as the angle. So that relationship only is used to define a unit cell, and the crystal systems is defined by symmetry, not by the unit cell. So this is a major thing I want to highlight in this particular lecture, that the crystal system should defined by symmetry, not by the unit cell. So this is a mistake generally people do in their regular understanding of the crystal system. In future we will discuss why there are different lattices are absent in different crystal systems. Thank you for your support, and if you want any further videos and any content, you may please leave a comment in the comment box. Thank you so much.